Good afternoon, everyone. So very well welcome. So probably we have lost some of the colleagues, but hopefully we can take a recording of that, right? And
yes.
So that people who miss this session could listen later. And so basically very warm welcome to join the Supergen webinar on this whole system analysis of thermal energy storage technologies in future UK networks. So I'm Jianzhong Wu, Professor of Multi-Vector Energy Systems at Cardiff University. So I'm leading the multi-vector energy infrastructure work package in APSEC Supergen Hub on energy networks. So it's my great pleasure to chair today's webinar. Yeah, if colleagues could mute, that would be great, thank you. So we have 3 speakers today, and I will introduce them using the running order. So Dr. Adriano Sciacovelli, and who is a lecturer in chemical engineering at the University of Birmingham. He has extensive expertise in clean energy storage, energy processes, and process optimization. He's an investigator on several APSEC projects, focusing on decarbonizing of heat and thermal energy storage. His research on thermal energy systems and optimization has received the Edward Albert Award from the American Society of Mechanical Engineering. So welcome, Adriano. And the next speaker, the second speaker is Dr. Alejandro Gallego Schmid, who works as a lecturer in circular economy and the life cycle sustainability assessment at the University of Manchester. He's part of a Tidal Center Manchester, where he works identifying sustainable solutions for industrial, water, and energy systems on a life cycle and a circular economy basis, taking into account economic, environmental, and the social aspects. Welcome, Alejandro.
Thank you very much.
And the last speaker, but not the least, is Dr. Hossein Ameli, who is a research associate at Imperial College London. His research is mainly focusing on facilitating cost-effective transition to low-carbon energy systems through the employment of flexibility options in the integrated option and operation and the planning of different energy vectors, mainly including gas, hydrogen, heat, and electricity. He contributed to many projects related to energy industry, such as projects for BASE, committee for climate change, and oxygen as well. And welcome. And please join me to welcome all speakers. So we will have a dedicated question and answer section after the PPT presentation. Please feel free to leave your question at the chat area, or you could raise your hand during the discussion as well. So I will invite you to unmute yourself and raise your question. So I will also ask whether there's any burning questions after each speaker's talk, so that we can have some timely interaction. So the section will be recorded, just to remind everybody again. And I hope everyone is okay with this. But if you have any concerns, please either contact Linda, who is online, or contact me. And this is all I have to say at the front. So probably we need to press on. I would like to hand over to Adriano.
Yeah, thank you very much, Professor Wu. I'm gonna jump in and share my screen and go ahead with my presentation. So please, if you see my presentation.
Yeah, we can see it.
Fantastic. So thank you very much again. I'll present this project that was funded by the Supergen Energy Network, and as you've heard, it's a collaboration between myself, my team at the University of Birmingham, Alejandro Schmid from the University of Manchester, and Hossein Ameli at the Imperial College London. So I would like to spend this 10 minutes presentation in essentially introducing the project and thank you. Let's appreciate what are the objectives and motivation in the context of the Supergen Energy Network Hub, and discuss the, let's say, present the specific contributions from the University of Birmingham in this project and how these feed into the work of the other colleagues here in the call. So let me start from the indeed objectives and motivation of this project. So this project focuses on assessing and understanding the let's say, whole system value of thermal energy storage technologies in future UK energy networks. And in particular, we focus on understanding what is the role of thermal energy storage in managing interactions between electrical network and the heat sector, both let's say distributed heating system at domestic scale as well as industrial and district heating scale. In doing so, we have been interested in understanding what are the key technological parameters that drive the value in the thermal energy storage technologies, and ultimately, but more importantly, in assess what is the impact, the whole system impact of thermal energy storage technologies and the life cycle impact. So in particular, how the carbonization of the UK energy networks can be facilitated by thermal energy storage technologies, as well as what is the sustainability of these solutions. And as you see here in this schematic that Hossein has kindly passed, the focus will be on this, let's say, part, so on the role of thermal storage, but with a focus on how these part of the possible portfolio technologies interacts with the whole UK energy system. So, as you might appreciate, this obviously requires, let's say, research and operating on different axes. So, from the University of Birmingham, we focus mostly on the technological and techno-economic characterization and reduced models of specific thermal energy storage technologies, which I will discuss in a little bit more detail later on. And these, let's say, technical and techno-economic information is, let's say, shared and exchanged in a, let's say, bilateral way with both the investigation at the University of Manchester regarding the life cycle analysis of these of such technologies, as well as the integration of these models of thermal energy storage technologies in the whole system and modeling platform developed at the Imperial College, with ultimately the aim to understand the impact and the value of thermal energy storage technologies when, let's say, deployed across the United Kingdom and across different regions. And obviously, one of the key ambitions here and objectives of this project is not only to obviously carry out this piece of meaningful research, but is also to bring to the Supergen Energy Network Hub a set of specific expertise on such technology and such approach to obviously contribute to the ambition and the objectives of the Energy Network Hub. So I would like to then spend the next few slides on commenting and presenting the precise contribution and work that is going on from our side at the University of Birmingham, and how this feeds into the work at Manchester and Imperial College. So we are focusing this project on two specific class of technologies. We are focusing on the latent heat thermal energy storage technologies, as well as thermochemical energy storage technology. So we are focusing on near-to-market solutions, namely the latent heat storage systems, as well as storage solutions that are in, let's say, R&D stage, which are the thermochemical energy storage. And we use instead sensible, conventional, and well-established storage technologies as a baseline for cross-comparison of the impact of latent heat and thermochemical storage options. For those of you who might not familiar, the latent heat storage options operates by, let's say, working principle of melting and solidifying suitable materials, which are called phase change materials. So heat or cold is stored in the form of latent heat, while thermochemical storage systems exploit reversible chemical reactions. So here heat is stored in the form of chemical bondings, and therefore they allow, let's say, higher energy storage densities, and as well as longer duration storage. So the work at Birmingham has been focusing on extracting the key techno-economic parameters of these two technologies, as well as producing reduced models that can support the life cycle analysis and the whole system analysis carried out at the other two institutions. So on this slide, as exemplar cases, you can see at, let's say in this case, a laboratory scale, how a latent heat thermal storage system might look like. So what you see here on the top left is indeed a small-scale device that exploits latent heat to store heat. So this white substance here is a phase change material in the solid phase and is indeed solidifying to store heat. On the right-hand side, you see a thermochemical storage option. These are salt hydrates that allows to store heat by reversible reaction of hydration and dehydration. The key here, obviously, in this project is not on technological development, but on extracting the right and accurate techno-economic parameters and models so that the life cycle analysis and the whole system analysis is grounded and based on let's say, meaningful technological data. So we have developed a, let's say, procedure to indeed extract these techno-economic parameters, starting from the development of a comprehensive database that covers multiple implementation of these two technologies, of latent heat or thermochemical storage technologies. So we are focused mostly on, for the latent heat, on systems that are suitable at domestic scales. So we are talking about systems that are using PCMs that are paraffins or fatty acids with a temperature, storage temperature that is typically from sub-ambient temperature for cold storage to about 100, 120 degrees C. While for the thermochemical storage system, we have been focusing on salt hydrates, which are the most suitable one for domestic applications. And let's say, techno-economic database starts from a selection of a candidate and assess the typical requirements for thermal power and hour of storage, and then identifies the necessary volume of the storage system, as well as the possible geometrical configuration, and ultimately produce reduced numerical models that can be integrated in the whole system analysis, while the techno-economic parameters can be easily included in the life cycle analysis. So I'll take a couple of exemplar cases of how these techno-economic results appears in our study. So what you see here are two exemplar cases of the range of techno-economic parameters that we are extracting to support the analysis. In particular, for sodium acetate trihydrate, this is a typical phase change material that is quite, let's say, has a quite good range of energy storage density, power density, as well as cost, while magnesium chloride is a typical thermochemical storage material used in thermochemical storage systems, and that allows sufficient energy storage density and relatively compact solutions that are suitable for compact storage systems. So these are the typical techno-economic parameters that we are putting together and to support the life cycle analysis. While for the reduced modeling approach, we have been essentially developed together with the colleagues at Imperial College a mixed integer linear programming framework of reduced model of thermal storage that allows to embed the key performance indicators, namely energy storage density, maximum energy stored, volume of storage system, into the whole system modeling. A key feature also this reduced model is that, as you will hear later on, allows to actually account for different type of storage systems that might be distributed at different locations across the UK. And this is captured essentially by a parameter that allows to distribute the best storage system in, let's say, the best location across the UK. So this brings me essentially to my last slide. So just to reiterate, the project addressed the whole system role and value of thermal storage technologies, particularly PCM-based and thermochemical storage-based. And at the University of Birmingham, we are focusing on the techno-economic parameters and reduced models to support the life cycle analysis and the whole system analysis. So I stop here, and I thank you very much for the attention. I'll pass it back to Professor Wu for the next step.
Okay, many thanks, Adriano. So it's really interesting. Thank you. So any burning questions? And as I said, we will have some dedicated Q&A section at the end. And I haven't seen anything from the chat area. If anybody got any question, you could use the raise hand function. It's a blue hand at the right-hand side. I haven't seen anything. Probably we can carry on. So the next speaker is Alejandro. So I just hand over to Alejandro directly. Yeah.
Thank you, Professor.
Thank you.
I hope that.
Yeah, we can see your slides now.
Okay. So, yes, 1 second. Okay, so I'm Dr. Alejandro Gallego Schmid, and I'm gonna be talking about the work that we have developed regarding life cycle assessment of a phase change material, PCM head storage system. This work has been done in collaboration with Daniel Chiconta, Dr. Muñoz, Dr. Manente, Dr. Adriano Sciacovelli, and Dr. Hossein Ameli. So the outline of this presentation, I'm going to start presenting the concept of life cycle assessment, LCA. I'm going to be talking about the main environmental impacts that we can calculate with LCA and some of the most common applications of this tool. After that, I'm going to be focusing in the work that we have been developing in this project, which is the LCA of a PCM head storage system. This is a work in progress, so I'm going to present just a snapshot of what we are doing at the moment. So far, we have been defined the system boundaries and we have collect all the inventory data. And finally, I'm going to present the next steps that we are going to be doing in the following months. Life cycle assessment is an environmental sustainability tool that allows us to calculate or quantify the environmental impacts of different product, processes, or services, and it's based in the concept of life cycle thinking. And maybe the next question that you have is, what is life cycle thinking? So with an example, for example, myself as a consumer, I have bought the laptop that I have in front of me, but if I start to think what are the impacts that this laptop has, maybe I just only realize what I see, which is maybe the impacts of taking my car to go to the shop to buy the laptop. If I think a little bit farther, the electricity when I'm using the laptop can have some environmental impacts. And obviously, if I go a little bit farther, is what are the impacts associated to the end of life of this laptop? What happens regarding the different materials, if it goes to recycling, to landfill, or to incineration? But obviously, there is much more, and that's the concept of life cycle thinking. Okay, so we have all the impacts associated to the life cycle of the product. Okay, following the same example, it will be the copper that is used in the electronic part of the laptop. We have some impacts associated to the extraction of that copper, to the manufacturing of the electronic parts, or something similar with the plastics that it's part of this laptop that we have taken as an example. For example, we have as well all the emissions associated to the transport of those materials and the electricity and heat that we use during the whole process. So that's the concept of life cycle thinking that I think is very well summarized in this final image, where we consider in the case of that we are doing a life cycle assessment with the environmental part, we are considering all the impacts associated to the extraction of the raw materials, to the production, to the distribution, to the use, and to the end of life of a product. But as I mentioned before, it can be applied to a process or a service, for example. So basically, LCA, what it does, first of all, what we do, we quantify all the environmental burdens of this product process of activity. So we collect all the energy and materials used and waste released to the environment. And we quantify the environmental impacts by translating the burdens into potential impacts, as we are going to see in the next slide. And that allows us to identify opportunities for environmental improvements along the whole life cycle of a product process or activity. So one of the questions can be, what environmental impacts do we consider? With the methodology that we use, we are able to calculate up to 18 different environmental impacts. Okay, you have some examples over there. is acidification, eutrophication, resource depletion. Maybe you have heard already the concept or the term carbon footprint. Carbon footprint is nothing else than an LCA that is applied only to one impact category, which in this case is climate change. So let's see how we do this, how we translate the inventory in final impact. So here we have an example. Okay, let's see that these are the inventory that we got from our process. Okay, so the first step is to try to classify these emissions or these components according to the different impact categories that we have. Okay, so if we have emissions associated to CO2, to methane, or to nitrous oxide, okay, all those emissions contribute to global warming. Okay, regarding the impact category of resource depletion, in our example, we have fossil fuels like oil, natural gas, and coal. For eutrophication, we consider all those materials or compounds that have nitrogen and phosphorus, because those components those are the components that contribute to eutrophication. And in the case of human toxicity, from our sample, we have some compounds that can contribute to human toxicity, like, for example, arsenic or benzene. Okay, again, this is an example for 4 impact categories. As I mentioned before, we are able to calculate up to 18. So the next step is try to characterize or do the characterization, with this basically to translate all these different emissions or products in a common unit for each impact category. In the case of global warming, the the unit that we use is kilograms of CO2 equivalent. And thanks to the characterization factors of the International Panel of Climate Change, we can translate all those emissions in this common unit. For example, we know that 1 kilogram of methane produces the same impact factor of from the point of view of climate change as 23 kilograms of CO2. So with that characterization factor, we are able to express the emission that we have in kilograms of CO2 equivalent. Similarly, is done with the other impact categories, obviously with different units. Okay, so that allows us to calculate the different impacts. So something important as well, and I want to make clear that we are from the University of Manchester. We are always open to collaborate, particularly with all the components of the hub. So what things can we use this LCA? For example, imagine that you have a new technology that you intuitively think that can be better from the environmental perspective. Okay, so what we can do is we can quantify that. We can put into numbers. Okay, for example, comparing this new technology with the business as usual. Another option is, if you want to know what are the hotspots of your technology or your product, what are the 2 or 3, 4 things that contribute to most of the impacts, okay? In order, obviously, to focus in those hotspots, the potential improvements that you want to apply. And the other option is that I have been focusing in this presentation in the environmental perspective, but obviously life cycle thinking can be applied also at social and economic perspective, okay? In the case of social perspective, we talk about social LCA, and in the case of economic, we talk about life cycle costing. So another option is to do a multi-criteria assessment considering environmental, social, and economic aspects, okay? So that's something, for example, that we have done in the past to assess the sustainability of the electricity system in Chile. Okay, so now I'm gonna focus in the second part of the presentation on the specific work that we have been doing in this research project. What we are doing at the moment is the LCA of a PCM heat storage system. And basically we have considered a system that is cradle to grave. So we consider all the stages of the life cycle of this system, and we have considered the extraction of the raw material, the impacts associated to the production, as well as the impacts that happens during the installation and use, and even further than that, what impacts are associated to the decommission and what happened with those materials at the end of life. Okay, and so in some cases we can have what is called a closed loops through recycling, and some of these materials can go again into the system, and that's the reason that we have this arrow here. Okay, so we have considered that this PCM heat storage system that we have here, also considering solar collector circuit, obviously the PCM units and a water tank. According to the literature, we have considered that the life expectancy of this system is 20 years, which applies to most of the parts of the system, except for the chemical part, the PCM components that we have established 10 years for the heat transfer fluid, 3 years for the pumps, 5 years. Okay, so basically we have here the amount of raw materials that we need for each component for this 20-year period. We have considered initially two compositions, both for the chemical part, for the PCM, and also for the infrastructure, let's say, of the PC unit. So we have, I'm going to focus in this presentation in the first composition, which is PCM1 and PCM tank 1. Okay. For the rest of the parts of the system, you have also here the inventory of the different materials, in this case for the solar collector, but also for the pumps, piping, hot water tank, heat exchangers, valves, and expansion vessels. So if we put all of this together, we can see that there is 17 types of materials. The most important regarding the weight is the chemicals, mainly through one of the components of the PCM, the SAT. Okay. Also, we have 5 types of metals. In this case, is mainly associated to the infrastructure of the PCM units, and also associated to the water tank. We have glass, which is quite important in weight and is associated to the solar collectors. We have different types of plastics, and finally we have stone wool, which is used as an isolation system in the water tanks. Obviously, we have other stages of the life cycle assessment that we have to consider the production of all the parts of this system, with mainly we have seen that is energy, what we are consuming, heat and electricity. As well, we have to consider the transport by truck, ship and train, because obviously there is emissions associated to this transport. We have to consider the installation and the commissioning, which in this case, we have decided to consider that the impacts are negligible, because most of the work is going to be it's going to be manual or with small tools. Regarding the maintenance and use, it's very important, the life expectancy that we are going to be considering, and we got all the data based on what is available in the literature. And regarding the end of life, we have considered that this system is in the UK, so we have taken into account the average UK values for recycling, incineration, and landfilling for each raw material. And something that is common in LCA, we have considered a distance from where the waste is produced to the waste management facility, an average of 50 kilometers. Okay, so finally, for the other parts of the system that are no raw materials, here you have the final inventory. In this case, we have considered a functional unit, or the unit that we take as a base to calculate this. In this case, is 1 kilowatt of energy, in this case, heat storage. And you have here per kilowatt hour of this heat storage, how much do we spend in energy, in the production, transport, and what happened at the end of life with the different materials. So sadly, we were not able to bring to this webinar the final results of the impacts. We are still working with them. We are almost there. So the next obvious step is to finish the calculation of these impacts and start to see the interpretation of the results. This will we have start to see that the chemicals and the infrastructure can be the potential hotspots, and from there we will look for potential improvements. One of the options is what I mentioned at the beginning, is to consider other configurations that are available for those chemicals and for the infrastructure, as we have over here. And also another option is to compare with natural gas and electricity, how the same amount of heat is produced by natural gas and electricity. Further the line, we also want obviously to calculate the environmental impacts of introducing this kind of systems in the whole energy system of the UK, which is what my colleague Hossein is gonna be presenting in the next presentation. Many thanks for your attention, and I will remain attentive to any questions that you have.
Okay, fabulous. Thank you very much, Alejandro. So I think there's one question in the chat area, but what I found is this may not be directly relevant to LCA. So probably if that is okay, I will keep it. In the Q&A section, we will discuss this properly, if that's okay. I haven't seen other questions, so probably we can carry on. So next speaker is Hossein. So I would like to invite Hossein to give a talk.
Yeah, thank you. So let me just share my screen first. So
yeah, we can see your email. Oh, now it's okay. Good.
Okay,
yeah.
perfect.
That's good. Thank you.
Yeah, so, okay, good afternoon, everybody. So this is Hossein Ameli, and I'm here to present our work in the whole system analysis of this thermoregulatory systems. And we worked in this with he is my colleague at Imperial, and also Adriano and Alejandro. Also, we are just providing this stuff. So let me just have a quick look on the outline of the work. First, I want to introduce what are the whole system components, then talking a bit about the sector couplings, then the interaction of the energy vectors and how we do the whole system modeling approach it is, and then we just consider two cases to let's say quantify the value of the thermal energy storage systems, hot water tanks, PCM and TCM from the whole system perspectives. So, of course, we saw this figure before in Adriano's presentation. This is actually what are the whole components that we could have in our modeling and the whole system perspectives that as we can see, there are some parts in it related to the electricity side, the heat network and the gas network. And the focus here would be mainly on the TES block to see what is the value of this technology from the whole system perspective, just to see how this flexible option can provide flexibility to the other vectors, and what is the benefit of having different type of TES in the whole system model. So here we are just going more focusing on the heat and electricity network. As you can see in the figure, it is shown that we have, let's say, the spatial granularity from transmission to low voltage distribution on the electricity side, as well as we have the heat network, and we can see where are the interactions and what are the coupling components, which can let's say, increase the interaction between these two vectors. And as it is mentioned, the demand side, let's say, if we have the preheating, can further, for example, enhance the flexibility in the electricity system. And in our analysis, we demonstrated that if we have in the planning of these two systems, if we have an integrated planning for heat and electricity, we can, let's say, the flexibility in the heat system can provide significant savings in the electricity system, since let's say we reduce the reinforcements costs in the electricity side. But if they are planned separately, this will incur dramatic costs as well associated with flexibility compensation. And what is the necessity of the whole system modeling? Let's say first, in this option, we could see the interaction between different level of assets. Investment in one infrastructure can potentially influence the other energy vector, and we will see both, let's say, operational and investment timescales from seconds to year, let's say, and this can be also been considered. And one aspect that kind of makes this very important, this whole system modeling, is the electrification of the end use side, because this will result in reinforcement in the distribution network, reinforcement in the transmission network, investment in generation, and also less investment in the heat network, because we kind of will provide the heat by electricity. So this will have all these interactions, and therefore it's necessary to have this whole system model to cover different level of infrastructure across different energy vectors. And the aim is here actually to minimize the both operational and planning costs of the whole system, including electricity, heat, and also it might be the gas, hydrogen, and etc. And in the whole system modeling, we have the spatial granularity and the temporal resolution are presented. That, for example, we have it from local level infrastructure to national level, and in our case, that here we want to present. For example, the national level is divided into 4 regions and is modeled by 4, let's say, nodes. And the timescales are also been presented, that from a few seconds in order to have the frequency response regulation requirements, to hours, which is mainly for the unit commitment and the dispatch of the energy, to yearly time horizons, which is mainly for the planning side of the modeling. So let's just go through some results, which is mainly, these are provided by my colleague Xi, which he did the simulations. And this is kind of showing the whole system benefits of using hot water tanks. And it is shown that we have here 2 scenarios, one for 25 grams per kilowatt hour, and another was the 50, let's say, emission targets. And it is shown that if we have TES, we can have, let's say, we are having annual savings. And the increased cost would be for more renewables, we have more backup capacity, and obviously more thermal energy source systems. But the savings would be on other components like the NUCs, CCS, this capacity of heating appliances such as heat pumps, distribution network reinforcements, and these would be all the savings. And if you see in the figure, the black triangle is kind of showing the overall savings that we could achieve in both cases. And as we can see, if you just want to go to, let's say, lower carbon emission targets, we could save more through this flexibility, which is kind of this flexibility in the heat system will provide overall more savings in the whole system consuming electricity and heat. Then here the focus comes to TCM and PCM, which is the mainly work that we have done with our colleagues mainly at Birmingham and also Manchester, that they provided us some inputs in terms of the energy density, capex, and the volume of the thermal energy storage systems. And then we run just some sensitivity analysis just to see how different parameters can impact the whole, let's say, the value of the thermal energy storage systems from the whole system perspectives. So this case, kind of, we are showing the economic performance of TS. The red box is the assumptions that we used in our modelings, and it is shown that if we have PCM only scenario, this is the most, let's say, cost-effective case that we got the most savings, and we need to kind of install 42, the penetration level in the households would be 42%, and the PCM should be, let's say, installed there. But for the TCM is only 4%. that's going to be the main reason due to the higher energy density that TCM provides, but the savings are less compared to the PCM case. Now here we just focus more on the sensitivity analysis. In this one, we are seeing how should be the proportion of each of these technologies in terms of the TS penetration level into the households, let's say. And it is shown that, for smaller penetration levels, for example, 10%, we should go more for TCM. But if this penetration level increases, let's say the value, or let's say the role of PCM will increase, and even after in 25% we can see we just go 100% with PCM, and we don't need to do any TCM, and the green kind of line is showing the total cost of the system. And so for conclusion here, we could say that when the TS penetration reduces, the advantage of TCM is getting more significant compared to PCM. But if let's say we increase the penetration level, it's the other way around. Then now here we consider kind of two parameters, the penetration level as well as the volume. We have here two cases for the volume. That's in the first, let's say the top figure, we assumed 0.5 cubic meters, and in the bottom case is 0.4 almost cubic meters. And kind of it is shown that here that when the TS volume reduces, again, the advantage of TCM is getting more significant compared to PCM, which that's again mainly due to the higher energy density that TCM has compared to the PCM based on assumptions. Then in this one, we are considering the penetration level and the energy density, and it is shown that for higher energy density, it gets more for the PCM, because as you can see in the, for example, if you want to compare the 25% in both figures, we see that the proportion of PCM in the top figure is almost 80%, but in the bottom figure is nearly 35%. And this shows that the TCM has, let's say, can play a more important role if the energy densities are lower. But for higher energy densities, PCM has more advantage. And the last thing that here we considered was, again, the penetration level and the CapEx, the capital expenditure or the investment cost, which shows that if we have lower CapEx, TCM has more advantage. Again, if you just, for example, if you compare the 10% penetration level of TS, it can be seen that in the top figure is nearly 25% of PCM, while in the bottom is less than 10% of PCM, and TCM can kind of make a better role from the whole system perspectives. And yeah, then that's it, kind of what we have done so far in terms of the optimization and simulation that has been carried out. And just some remarks on future work. In this one, let's say we considered the end-use TS technologies, PCM and TCM. And with our modeling, we were able to kind of optimize the proportion of each of these technologies, let's say across the GB. It was 27 million households, I believe. Let me just, yes, 27 million households. And the proportion has been presented based on different assumptions and based on different parameters, which was the CapEx, the energy density, and the volume. And for the kind of the future work, first of all, still working on the end-use TS, let's say working more with our colleagues at Birmingham and Manchester to get, let's say, more precise parameters to just do the modeling. And also it's important to analyze the whole system benefits of industrial size of TES, which these would be typically applied in discrete heating networks, and also considering more the spatial distribution of different types of TES, and depending on the geographic areas like the urban, rural, suburban, subrural, because obviously in different geographic areas we could have different let's say use of heat, and so therefore the, let's say, the mix and the optimal proportion of these technologies might be different. So we are keen to consider these and just do the modeling. So that's it from my side. Thank you very much. And sorry if I mentioned any TC and PCM wrong, because they are very close letters, so it might be some mistakes, but I hope it was all fine. Thank you very much.
Many thanks indeed, Hossein. So really interesting. So now I think it's time for us to have discussions. And I know we're running late. So if everyone is okay, so we'll stay a little bit longer. And so we can spend another more than 10 minutes to have a quick discussion. And but if you have something else I'm urgent to deal with, feel free to leave. And this one question left by Paul. And the question is about how does it work compared to the development of heat batteries in Edinburgh, which has been commercialized. So could I invite the team to respond to that?
Yes, perhaps I take this question. So as probably has been hopefully a little bit more clear once we went through all the presentation, the work here focuses on the value at system level of the thermal storage technology. So in this sense, it's not focused on technology development here, but rather complements work that has been done from technological development perspective at Edinburgh, but also elsewhere. So in this sense, as Alejandro and myself presented, we are including in our modeling work PCM that are indeed those that have been also considered by Sanam. And beyond that, we are also considering thermochemical storage options. But the focus is on assessing the whole system or system value rather than on the technological development.
Okay, thank you. I hope that this answers Paul's question. So if not, please do raise your hand and have a discussion here. And while we're waiting for other questions, I have a very quick question. And for such thermal storage, we can see clearly there's a value there. And so the results showing is really interesting. I'm just wondering, in real world, so how this thermal energy storage perform will be determined by how it is controlled or how it is used. Different control may have different cost associated with that. So we'll have different impact. I just wondering how these are considered in the current study.
I'll try to take this one as well, if it's okay, or
yeah, no problem, no problem. Yeah, probably
can comment on this one, perhaps, if it's on the cost aspects. But yeah, let's say control strategy and control aspect are certainly relevant in the PCM systems. We are not, let's say, currently taking into account specifically the let's say embedded cost of a control strategy or control subsystems, if you prefer, but those will be part of the, let's say, one of the elements in the life cycle analysis, and particularly the material that goes into those elements. While in the whole system modeling, we will be able to account for those costs in the OPEX whole system cost that we are currently, let's say, considering in that modeling framework.
And one other aspect that I want to add, if you don't mind, is that, of course, since we kind of do have these as input data, we can also see it another way around and even also optimize, let's say, what should be the associated cost or the optimal cost of different technologies to have the most benefit from the whole system perspectives. And this is kind of what we also can consider in this, let's say, project, and then see how is it possible from the LCA analysis or from the technology side development, let's say, being, let's say, plausible to reach this cost or something like this. Yeah.
Okay, thank you. So this, yeah, please, yeah, Alejandro, yeah.
From the environmental perspective point of view, obviously, the way that you manage the system may influence clearly the final environmental impacts. Obviously, from the perspective of the maintenance, for example, is crucial, no? Because as what we are seeing in the results is that the impacts are not so much associated to the use itself, but to all the materials that you are consuming. So at the end, if you don't do a proper maintenance of the system, that is going to imply that instead of having 20 years of lifetime expectancy of the system, you are going to have much less. In order to cover those 20 years, you are going to need much more materials. And obviously that's going to imply that the environmental impacts of the whole system is going to be much higher.
Okay, thank you. Thank you very much. So these are two further questions. One is from Hector. And so this is about detailed modeling. So probably it's Adriano's question again. So this is about how difficult to obtain the specific heat of enthalpy of a new PCM.
Yeah, I'll address these questions. Thank you very much for the question. So for well, new PCM, let's say typically there are two avenues. Either is equilibrium thermodynamic calculations with, let's say, mixed or weighted average thermophysical properties. For example, if we are using PCM with a supporting matrix, the latent heat will be basically a weighted average of those two components. On the other side, let's say experimentally, that can be done with differential scanning calorimetry techniques. For this specific work, what we are doing here in this project at the University of Birmingham, we are using a blended approach where we have a quite extensive characterization of materials that has been put together over the years here in the labs at Birmingham, that we are complementing with, let's say, thermodynamic theoretical data to take these parameters and feed them into the life cycle models and the whole system models.
Okay, thank you very much. The next question is from Matt. So this is to Hossein. So this is regarding how to use this thermal storage for frequency response, because clearly it's not directly linked together. So how you imagine your model to consider this?
Yeah, well, in this case, kind of the TS has to be used with the electrified heaters, such as heat pump or resistive heaters, to provide the frequency response. And it's just not only the TS would kind of indirectly supporting the frequency response. But yeah, my colleague is also here. Do you have any other thoughts to just complete this, or that's what you think?
Hi, I'm Shi. I can give some more thoughts about this question.
Thank you.
I think TES just serves as a link between electricity and the heat sector. So when we want to use TES to provide the response, then we have to use it with heat pumps or resistive heaters. So we can just reduce the power output with the heaters, and then we can store energy in the TES. And when we want to provide when we want to provide the frequency response, then we just need to reduce the power output of the heaters so that the energy can be balanced. But this has to be finished with the support of TES. Otherwise, the reduced power will not be stored. So it works pretty much as the batteries. The battery can be directly provide the response within the electricity sector, but we can use TES to bridge the electricity and heat sectors. Okay.
Okay, thank you. So actually, this is related to the question I asked before, how this be used or controlled. And so there's some research there to look at, for example, if you have a district heating system powered by CHP. So the CHP could provide more support to frequency response. Then they will change the electricity output. This will impact on the thermal part. So if you coordinate with that one, actually you could indirectly provide frequency response by CHP, but you can use heat storage to balance the heat side. So that is something could be explored that could have some added value to the thermal storage. But clearly that is more complicated because it's not a direct link, not like heat pump. But it's really interesting work. Yeah. Good. And I haven't seen further questions. So if that is okay, I would like to take the advantage of a chair to ask one last question. So I thought, for example, Hossein part is look at whole system analysis. Alejandro is look at life cycle assessment, how you two embed together? Do you have plan to integrate something together? Because you have different focus clearly, but I think both are very valuable work. I'm sure both of you will take input from Adriano, but how you two will integrate is not immediately clear to me. Yeah.
I can start the answer, and maybe Hossein can complement it. Basically, the idea is at the end is integrate as well the life cycle assessment of these technologies and to see how it will affect the whole system. Okay, so kind of to upgrade it at the system level of the UK and see how it's going to be the effect compared with other potential scenarios. Okay, but obviously in order to do that, first we have to do the life cycle assessment of these systems, and from there we will see to what point we can substitute other alternatives with this one, and see how if it improves or not the environmental performance of the whole system. But that's something that we are going to be doing later on when we have very well defined what is the environmental impacts of the technology or the system at more like just focus in the system itself, and then try to upgrade it or to put it more at the level of the whole UK system.
Thank you.
Yeah, and what I wanted to add is that since we are also kind of doing a planning and investment on thermal storage and from the whole system perspectives, two aspects that I was just thinking was that, first of all, due to the LCA, we can get probably exact or accurate numbers in terms of the emission produced by, let's say the TS life cycle assessment. That can be considered in our modelings, because we usually always have the emission targets, and based on that we should have for different components the emission that they produce, or let's say has been produced to, let's say, have manufactured the component. That's one aspect. The other aspect is that that's also the lifetime of the assets is very important to us, so we can take into account in our investment model. And that's also, again, something that Alejandro's team can kind of provide us with more accurate, or let's say numbers that we can also use to kind of conduct our modelings. Yeah.
Okay, excellent. So thank you very much. So I'm conscious of time. So I enjoyed the presentation and the discussion very much, and I hope you feel the same. And please join me to thank all speakers, and many thanks to all of you, to all of you for your participation as well. So I would like to close the webinar now, and all the best, and keep in touch. Thank you very much. Thank you.
Thank you. Thank you.
Thank you very much.
Thank you
Take care. Bye-bye.
Have a nice
Bye-bye.
day. Bye-bye.
Bye-bye.